Now that you guys have seen a couple of examples of probability assignments and how they can be used to calculate the expected value and standard deviation, what I want to go through now is a couple of problems where you can see how the expected value and standard deviation can be applied to the normal model. So remember, we used the normal model in the last exam, and we're going to bring it back here to answer more interesting questions. So let's say you're a grocery supplier or you work for a grocery store restocking dozens of eggs or cartons of eggs, and that on average the number of broken eggs is a half. Some cartons don't have any broken eggs, some have more, but the average is just 1/2. And then the standard deviation captures the fact that there's variation from carton to carton. And then you buy 3 cartons. How many broken eggs do you expect in those 3 cartons of eggs? Well, to answer this question, we can create a linear combination of 1 carton. So we can start this problem by defining x as the number of broken eggs in 1 carton. The problem gives us the expected number of broken eggs to be 0.5, and the standard deviation is 0.2, so I've written that here. But what we're actually interested in is 3 cartons, and so you can think of that new random variable as the number of broken eggs in 3 cartons. And that is just the linear combination of 3 individual cartons summed together. So here I've written x1, x2, and x3 to denote 3 separate cartons, 1, 2, and 3. So I'm not trying to multiply x by 1 and x by 2. I'm just trying to say that these are 3 separate cartons, but they all follow this distribution of having a mean of 0.5 and a standard deviation of 0.2. Normally I would write these values x1, x2, and x3. I would write the numerical values as subscripts, but the font on this doesn't let me do that. So I've just written the numbers next to x to denote each of those cartons. What we want to find next is then the expected value of those 3 cartons. And so we can just use our rules for the expectation operator of a linear combination of random variables. And the expectation operator says that we can take each of those separate cartons out and evaluate them separately and sum up their expectations. And so we can sum up each of the expectations. Again, they all follow the same distribution, that the expectation of 1 carton is just 0.5, and so this is just going to be 0.5 3 times, so our final answer is 1.5 eggs. The next thing we want to do is we want to find the standard deviation for the number of broken eggs in 3 cartons. And so that was just going to be the sum of the 3 individual cartons and trying to find that standard deviation. Again, we have to go through the variance operator to separate these out. We can't just plug in 0.2 and add that up. We have to go through the variance operator because that's where our rules apply. And so remember that the definition of the standard deviation is the square root of the variance. So that's all I've done here is use that definition. And then the next thing I do is I separate out those 3 individual variables, x1, x2, and x3. The reason why I can make this next step is because I am assuming the cartons are independent. So the number of broken eggs in 1 carton doesn't affect the number of broken eggs in carton 2 or carton 3. That's the assumption I make to be able to just add up these variances individually. The next step is to get back to the standard deviation. So remember that the relationship between the variance and the standard deviation is that the variance is equal to the standard deviation squared. So this next step, I'm just using the relationship between the variance and the standard deviation and rewritten it in terms of standard deviation. So now we have each of the single cartons separated out by their standard deviation. And we can simply plug in the fact that their standard deviation of 1 carton is 0.2, and then we'll square that for each individual carton, sum all of those up, and square root it. And that will give us the standard deviation of y, which is 0.3464. So now that you know how to calculate the mean and standard deviation of a new random variable, we can move on to ask more interesting questions that are maybe more applicable to real life. So let's say you select 3 cartons of eggs, and now what you really want to know is what's the probability that you get at least 1 broken egg or maybe more. We can use our normal model to answer that question. So the question we're interested in answering is the probability that our number of broken eggs in 3 cartons, y, is greater than or equal to 1. So we can notate it that way. The way we can solve it is by finding the z-score for that observation of 1 broken egg. So our observation goes first in a z-score, and then we subtract out the mean. And we have the mean for that random variable, and we also have the standard deviation. So when we divide by the difference by that standard deviation, we get negative 1.44. And we can use this z-score then to find the probability that y is greater than or equal to 1. We can simply rewrite our probability that y is greater than or equal to 1. It's the same as saying that a z is greater than or equal to negative 1.44, because this z-score is specifically associated with an observation of 1. And so these are equivalent statements, and we know from our z-tables how to find this probability. So we can use our z-table or our probability formulas, z-formulas, to calculate this probability. So to find that probability from our z-table, we're going to go down to the row that says negative 0.4, and then we're going to go to the column that is 0.04 for our second digit. And that's going to give us a probability of 0.0749. Now remember, the table gives us everything that's below, and we want everything that's above. So we're going to subtract this from 1. So the probability that we looked up, 0.0749, that's the probability that z is less than negative 1.44. But we want the complete opposite. We want the probability that z is greater than or equal to negative 1.44. So we can use our complement rule to find that. That's 1 minus the probability we just looked up. And so our final answer is going to be 0.9251. That's a pretty high probability that we would get at least 1 broken egg in a selection of 3 cartons. So let's try another problem that has constants in our linear combination of random variables, so you can see how constants enter into a factor. So here we have Janet, who rents booths at festivals so she can sell jackets and shirts. So she's an entrepreneur who sells jackets and skirts, and based on her past experience at festivals, she can figure out what the average number of jackets she sells and the average number of skirts that she can sell. And then she also has variation from festival to festival, and that's what the standard deviation is capturing. So sometimes she sells more than 7 jackets, sometimes less, and that's what the standard deviation is capturing. What we're interested in calculating then is what her expected income is going to be. Now it costs her money to rent a booth, and so we have to calculate out and figure out this new random variable of income. So we can start by determining the formula for income. The way we figure out income is total revenue minus the cost of operating this business. So it's going to be the number of jackets she sells times what she sells them for, so $190. And then the number of skirts she sells times the selling price of the skirts, which is $135. And then we subtract off the cost of operation. So income is just a linear combination of the number of jackets and the number of skirts that she sells. So we could just find the expected income by looking at the expected value of that linear combination. And again, our rules for constants and random variables apply here. So we're going to take out the constant terms out of the expectation operator and separate out the two random variables. So we're just left with the number of jackets, the expected number of jackets to sell, and the expected number of skirts to sell. And those are given to us in the problem, so we can simply plug those into our formulas at 7.3 for the expected number of jackets and 12 for the expected number of skirts. And that's going to give us a final answer of $2,907. That is her expected income. Now, of course, this is going to vary from festival to festival. Sometimes she might sell more jackets, sometimes she might sell more skirts or less skirts. It depends on the festival. And so her income is going to vary from festival to festival. And so our standard deviation will capture that variation. Now again, to find the standard deviation, we have to go through the variance operator because that's where our rules for constants and individual random variables applies. Remember that our definition of the standard deviation is just the square root of the variance. So that's all I've done here in this first step. The next step is to separate out these random variables, and we can do that by separating them out and assuming independence. So what that implies is that the number of jackets she sells does not affect the number of skirts that she sells. So we can assume independence and separate out those two random variables. So that's what I've done here in separating those out. Remember that even if this was a minus sign, this becomes a summation because we would be dealing with a negative term that gets squared. The other thing that I've dropped is this minus 100. And the reason why this gets dropped is because it's a constant that's subtracted from our random variable. And anytime you add or subtract a constant from a random variable, that gets lost because it doesn't affect measures of spread. So adding and subtracting a constant doesn't affect measures of spread, so we can drop that from our measure of spread. The other constant is multiplied, and so we have to take that in consideration, and when we move it out of the variance operator, it's going to get squared. So now that we've pulled the constant out of the variance operator and squared it, we're left with individual variances, and that's where we want to get to, because that allows us to convert the variance back into a standard deviation. Remember that the relationship between the variance and the standard deviation is that the variance is equal to the standard deviation squared. So that's all I'm doing, is I'm plugging in that relationship. And the same thing for the skirts. The standard deviation squared equals the variance, and so that's why I've plugged it in here. The standard deviation is what's given to us, and so we can go ahead and plug that in for jackets, which is 1.8, and for the skirts, that's 2.7. When I calculate this out, then I'm going to add up those multiplied terms and then square root it, and that's going to give me an answer of $499.82. So while she averages $2,907, there is some variation that's around $500. That's our standard deviation. So we can use these numbers to answer other questions. So maybe we're interested in answering a question that looks like this. What's the probability that she makes more than $3,000? So she needs to make $3,000 in a weekend because she needs to pay her rent or some bills. And so she wants to know what's the probability that she's going to make enough money to do that, so $3,000. We can use the expected income and the standard deviation of income to get a z-score, and then we can use that z-score to calculate this probability. This again is when we use our z-score, and remember that in calculating the z-score, we're going to put our observation first. That's what is given to us in the problem. We want to know the probability that she makes more than $3,000. So we want to find the z-score that's associated with exactly $3,000. We subtract then the mean, which is our expected income, and divide that difference by the standard deviation. That's going to give us a z-score of 0.19. So when we're saying we want to find the probability that income is greater than $3,000, that's equivalent to saying that we want to find the probability that Z is greater than 0.19. And we can use our Z tables to find this probability. And since these are equal, it's going to answer our question. So when we look for that probability in our Z table, remember that the first page gives us only negative scores. And we want to look for the score 0.19. So here on the second page, we find in the second row 0.1. That's our first spot. And then we want to go to the column of 0.09. And that's going to give us a probability of 0.5753. Now remember that the table gives us everything that's below that Z score. So that's giving us a probability that Z is less than 0.19. And we want the opposite. We want the probability that Z is greater than 0.19. So we're going to use our complement rule to find the answer to this. We're going to subtract that probability from 1, and that's going to give us a new probability. The probability that our income is greater than $3,000 is 0.4247. This probability actually tells us the probability that the income is less than $3,000. So this first one is the answer to our problem, and the second one is the complete opposite. So that's how you work through using the expected value and standard deviations to generate probabilities and applying the normal model to those random variables. In the next video, what I'm going to do is just a few more problems so you can see it in action.